Good afternoon, everyone. I am Dipanjan. I am a postdoctoral research associate in the fluid mechanics section of the Civil and Environmental Engineering Department at Imperial College. Today, I am here to give a brief overview of uDALES, a multi-physics microclimate simulation framework, and I'll showcase some of the validation/application cases that has been carried out using this code base. So uDALES stands for Urban Dutch Atmospheric Large-eddy Simulation. This has been forked from the legacy Fortran code that is DALES, and it has the capability of modeling most of the urban physical processes in an urban area. And then we have made appropriate modification to the DALES to make it specifically study the urban environments. So it has the ability to model the urban, airflow, heat transfer, radiative heat exchange, and heat storage in an urban building or in the vegetative surfaces. Also the pollutant chemistry and dispersion, effect of vegetation, and many other things. So uDALES basically performs the large-eddy simulation of the incompressible Navier-Stokes equation within the Boussinesq approximation, where the flow equations are discretized using the central reference scheme on a Cartesian grid, and the variables are arranged in a staggered manner. So the presence of these solid buildings in our fluid simulation are modeled using the image boundary method. So let's see how we do. So in uDALES, the building geometries are represented as a triangulated surface, where in terms of STL file format. So we have a robust preprocessing tool that takes these STL files as an input and the Cartesian grid, and then tags each of the grid points either solid or fluid. And then in the fluid points, we actually solve the Navier-Stokes equation. In the solid region, we just set the variable values to be 0. And then in the interface region, we use all functions to calculate the different variable values. Now, a key interesting feature or the novel feature that we have added to the DALES is this surface energy balance model. So here we solve the surface energy balance equation at each of the facets. Each of the facets. So where we solve we tell that at each of these triangular facet, the net long wave radiation and the net short wave radiation is balanced by the sensible heat flux and the latent heat flux, and then we solve the ground heat conduction to get an actual temperature of the surface triangular facets. So here, by long wave, short wave radiation, we means the radiation that is coming from the sun. So when the sunlight comes on the surfaces, they get heated, and every heat surfaces also again radiate long wave radiation. So thus every and then each facet receives long wave radiation from the nearby facets. So in this manner, each facet receives this short wave and long wave radiation, which we compute using the radiosity approach, and then every facet also exchange heat through sensible heat flux and the latent heat flux, and then this get balanced with this net heat received by the facet. Now, this surface energy balance model let us evolve the facet temperature with time and get the appropriate temperature of the facets. This surface energy balance model is two-way coupled with the image boundary method. So how we do it? That is, first we divide each of these triangular facet in small facet sections, and then we tag this small facet section with a particular fluid volume. So each of the facet section is tagged with a particular fluid volume. And then we use wall function to compute the shear stress and the sensible and latent heat flux for this small facet section, and then convert that fluxes to a volumetric source term to provide the to supply to the governing equation for this small for this small volume regime. Now, on the other hand, the surface energy balance equation are solved for the entire facet. So for that, the fluxes of this entire facet is the area-weighted sum of the fluxes of the small facet sections. In this manner, the surface energy balance model and the image boundary method, they become two-way coupled in a conservative way. That is, the net heating of the fluid is equal to the net cooling of the surface, and the entire area seen by the fluid is equals to the actual surface area of the facet. So this is how the main fluid and the solid coupling is being done in this uDALES. Next, look at the performance enhancement. So this code runs in MPI. So we use the 2D domain decomposition using the 2D compatibility library, where we divide the entire domain in small pencils and divide the domain in both X and Y direction to make use of more number of processes. So, and also for the pressure Poisson equation solution, we make use of fast Fourier transform using from the FFTW3 library to run it more faster. And we have observed that with this implementation, this code scales quite well. So for a problem with around 100 million cells, this solver scales very nicely up to 4,000 processes. And for a large problem like around 750 million cells, even for 16,000 cores, this code scales very quite well. Now, this was the basic overview of uDALES, and now I'll present some of these application cases that we have done. So first, I'll give example of some of the idealized cases. So to start with, it is the a neutral flow over a urban-like obstacle, that is an array of staggered cubes with varying building heights. In this case, we only simulate the airflow, so there is no the temperature equations are switched off. So for this case, we run, this case is around 17 million cells, and we run on the 4,000 processors. And here we present the domain average velocity profiles and the velocity profiles at the different locations within the computational domain. And we can see that the uDALES does a pretty good job in predicting those velocity profiles. Next, we have uDALES can model trees as well. So here we model the inertial and viscous loss due to the presence of the tree using a volumetric source term that has been added to the momentum equation. And here we are showing two cases. One is a single isolated tree, and here two rows of arrays of trees. And we compute the drag coefficient of these tree regimes and compare them with the experimental setup done by in the internal experiment by Fellini et al. And here we can see the uDALES observation with this magenta color stars. They are in good agreement with the experimental observation. So with appropriate setting, uDALES is also able to model the tree drag in an urban area. Next, this is an example that shows that uDALES can not only model the external flows, but also can model the indoor-outdoor flow interaction. To show that, we simulate a isolated building with two rectangular window at the windward and the leeward side of the leeward walls of the building, and so flow can go inside the building through the windward window and go out from the outward window. And here we are showing again the velocity profile and kinetic energy profile at different locations within the building. And again, the results are in very good agreement with literature, even for the inflow jet that is going inside through the window and the width of it. In both the case situation, it is able to capture all these physics very accurately. And then this is the example where we'll start. So all these example earlier, the temperature equation all was switched off. So we can switch off all these switch off or on as per our need each of these processes. Now this is the example where we switch on the temperature equation. So this case is the flow over an isolated building, but this time we use a constant surface temperature for all the surface facets. But in this case, we use inflow-outflow boundary condition, that is at the inlet of the computational domain, we provide a turbulent inflow, and then let the flow evolve as per the buildings inside the domain, and then the flow go out as a convective outflow boundary condition. Now, how we get this data? So for that, first we run a precursor simulation with a periodic boundary condition, and then take this output plane data and store it. And then next, when we run for the target simulation, we give the stored data as an input at the inlet. In this manner, we give a turbulent inflow at the for our main target simulation. Now, depending on the building geometry we choose here and how we nudge the flow within this precursor simulation, we can get a particular velocity profile or the kinetic properties as per our need, and this simulation can be independent of this main target simulation, but obviously it has to be done a priori because we need this data. So now going back to the actual simulation, here I will I'll explain what are these are the four arrangements. So these four are for four different simulations. So here original means in these cases the buildings are aligned with the Cartesian grid, and rotated means the buildings are at some angle with the Cartesian grid or the background grid where the flow equations are solved. And then in version 1, so these two, it means where the buildings are represented as voxel blocks or Lego-like blocks. So they cannot capture the rotation of the building, but here the buildings are represented as triangulated surface. So they can capture the rotation and the complex interaction between this background Cartesian grid and the solid surface. So if we look at the temperature contour, we can see that the voxel grid aligned case and the triangulated case, both aligned and rotated, all these three cases are in good agreement, whereas the voxel grid case under predicts the temperature contours in the leeward side of the building. And also here you can see the buildings are not very accurate and they are represented in a stepwise manner. Now, in this example, we do not keep the temperature of the facets constant, but we switch on the ACB equation as well. So we let the surface temperature to evolve with time. And in this case, we can see clearly see the temperature contour at the leeward side of the building is pretty significantly underestimated. And all the flux component, all the sensible flux component are underestimated specifically in the leeward side. However, the top roof doesn't get affected much because since the sunlight is coming from the top, in any rotation, the top roof gets the sunlight in the similar manner. However, for the backward leeward wall, get different prediction. So this shows why it is important to represent the complex buildings in an urban area very accurately. So next, to move some, all these are some idealized cases, and next we'll look at some of the more realistic situations. So here we are seeing a diurnal cycle of microclimate simulation. So what happens? The Earth's surface go a daily cycle as it receives, it gets heated by the sun in the daytime, and then at the night time it releases that heat, this stored heat in the night time. So such a diurnal cycle simulation of a representative urban area is shown in this video. And next we move a more realistic one. So here we simulate the atmosphere of the up to 1 kilometer height above the central London at 2 meter resolution. So to understand how the atmosphere behaves, and again in a daytime. So here we are showing a video up to say from 12 o'clock to 3 o'clock in the afternoon. And we can see that initially the flow temperature, the surfaces were cool, and then as the sunlight falls, these surfaces get heated, and then this makes the flow field turbulent, and which eventually interact with the comparatively calm wind at the upper layer. And in this manner, we can see this. How the surface energy balance about the surface heated surface affect the local microclimate. To give the scale of this problem, so this is around 4 kilometers. So it is around 2,000 points in this side, and this side it is around 2 kilometers, and then 1 kilometer. So this entire simulation domain size is contain around 700 million cells. And this, with more than 50,000 surface facets, that's making this problem a very large-scale problem. Now, this kind of large-scale problem with high-resolution simulation are very important to understand how the cities interact with the local microclimate, and this will help us to make decisions to and to make the future cities more resilient and more adapted to the future urban challenges like heat island effect and the urban poor air quality. So with this, I'll end my talk. So in summary, so we have developed a grid-independent geometry representation and a coupled conservative surface energy balance and image boundary method system, and which can capture the airflow and heat transfer for complex buildings in an urban area quite accurately, even for not grid-aligned cases. So we have also showcased a variety of application problems that can be done both idealized cases and the realistic approaches. So this is an open source research code that is available at this GitHub, and I would like to thank the RCS team specifically for the Imperial HPC support, and also to set up the GitHub page for the automate the continuous integration processes. And I'd also like to thank the Turbulence at the Exascale project from the EPSRC and the ACSC program for the funding support and the support to run our codes, our codes in the Archer 2. So thank you everyone for your patience.